Awesome. All right, so my name is MichaelNayak. I'm here for Dr. Ian Garrett Bethel, who is actually right now he's in South Korea talking to some folks at Kara about this mission. So I apologize in advance. I'm losing my voice. So it's a good thing I have a mic here that's so loud. All right, so today I'm going to be talking to you about Lunar Impactor mission that we're working on right now. And the goal is to impact a lunar swirl, which is kind of an enigmatic feature that I'm going to talk a little bit about, and see what science we can do at low altitude when it comes to paleomagnetism. So obviously there are a lot of partners that are working on this right now, including the University of California, Santa Cruz, which is who I'm representing, as well as the Imperial College of London, which builds the magnetometer that I'm going to talk about, University of California, Berkeley, that builds Cinema, which is the CubeSat you see over there. And what we're going to be using for the lunar impactor is very similar. The Massachusetts Institute of Technology, which is doing the propulsion system through the Space Propulsion Lab there, as well as NASA Ames. All right, so let's start talking about kind of the science of this. Really, it's a problem that goes back to Luna 1, which you see over there. The very first Soviet probe that had no cameras on it, just a magnetometer, and came back with the kind of surprising realization that the moon had no global magnetic field whatsoever, which is why it was even more surprising when Apollo went up that there were these local crustal magnetic anomalies that were detected by some sub-satellites that were kicked out by Apollo 16. And the origins of these are actually still debated. So I won't go into it too much, but essentially there's really two kind of predominant theories for this, for why this is. The first is that there was once a global dynamo on the moon that is now extinct. And then the other is that there were these giant impacts that happened kind of in the Imbrium-Nectarian era. And those were, all these swirls that I'm about to talk about kind of are antipodal to these giant basins that were created. So the question is, did that create this magnetism that we're seeing? Or is this just a remnant from a global magnetic field that once existed? So kind of the picture on the lower right there is from the Clementine mission. And that shows you a number of these patchy anomalies that we see all across the moon. In particular, it highlights Raynor Gamma, which I'm going to talk about some more, which is kind of the classic example of a lunar swirl. So essentially, we're trying to figure out what causes these magnetic anomalies. Does this link back to an extinct global lunar dynamo? And really what we need to know is, what does the magnetic field look like close to the surface? Right now, the closest reading that we have is at about 18 kilometers or so from low altitude passes during the lunar prospector phase. So more magnetic field measurements near the surface would help us to determine what the structure of the magnetic field is, and then try to link that back to, is this a global phenomenon that we're seeing, or is this something that's more impact-based? So with that, this is a good segue into lunar swirls, which, like I said, you see Raynor Gamma on the right, and superimposed over that are magnetic field contours in the horizontal direction. As you can see, there's a pretty clear correlation between the magnetic field that's underlying the surface and the actual dynamic of the swirl. So what is the swirl? Really, it's a high albedo feature set. This particular one is set in the lunar mare, and it's got really high reflectance values. And every lunar swirl that we see is correlated to a magnetic anomaly, though the opposite is not true. Not every magnetic anomaly exhibits a lunar swirl. So we're curious, what creates this? And kind of there are three different hypotheses for their formation. I won't touch on all three. I'll touch on the major one, but it's essentially that there is that these crustal magnetic anomalies are creating a mini magnetosphere. This mini magnetosphere is deflecting the solar wind flux. All right, so if you notice, there are some dark lanes that kind of cross through these bright patches. So the kind of the prevailing theory is that the solar wind flux, which, the constant bombardment of solar wind creates a darkening effect. So that darkening effect is being shielded on the bright areas, hence why they're bright. But that deflection is concentrating at adjacent areas, creating those dark lanes. So that's one of the theories. The other is obviously the impact theory that we talked about. That the opposite side of the moon, there was a giant impact, and that carried around to the antipodal side. So what we really need is near-surface particle flux and magnetic field measurements, and we need them below 3 kilometers, because some of the models that have been developed at UC Santa Cruz say that beneath 3 kilometers is where we'll really start to see some complex magnetic field structure starting to emerge. Right now, we just see those contours. And while those are descriptive, they don't really tell us what the source of this is, so it's still a mystery. So really what we're looking for is to get below 3 kilometers and discover what's going on at these swirls. We want to cross over the dark lanes, and we want to cross over the bright albedo areas. Now, obviously, the preferred solution would be a lander, but since that's really complicated and expensive, we're looking at a impactor. And kind of this is where the lunar CubeSat concept comes in, and we're using Cinema, which is developed at UC Berkeley, as our pathfinder. So this is NSF funded, about $1 million, with partners from Imperial College of London that built the magnetometers. And I'm going to talk about, show you a couple more details, as well as Kyunghee University in South Korea, which is where Dr. Garrick Bethel is right now. So the goal is to take this 30 centimeter 3U CubeSat, fly it on a low angle impact trajectory that's going to cross over as much of this swirl terrain as we can get. That's about 50 kilometers across right there. The radius is 50, so 100-kilometer long swirl. Try to get across as much of that terrain as we can before we impact, and send back high-resolution magnetic field measurements to determine what the origin of these lunar swirls are. And hopefully from there, extrapolate that back to a lunar magnetodynamic history. So how can we realize this with a 3U CubeSat? There's really 3 parts to this. So now I'm kind of switching over from more of the science side to the engineering side. The instrument, the magnetometer, propulsion, and navigation. So the magnetometer is based on the magnetometer that's flying on Cinema right now, developed by the Imperial College of London. As you can see, it's literally the size of a euro coin, so it's really compact. So one of these will be mounted on the spacecraft, and another one will be extended on a boom. And it's got below 2 nanotesla sensitivity, but more importantly, it's got a measurement frequency of 200 hertz. So this is obviously really important to us as we start to fly in on that low impact trajectory. We're moving at about 2 kilometers a second. So we want to get as much measurement as we can back as quickly as possible before we impact. So with 200 hertz, it is possible to get magnetic field measurements below 100 meters, which is actually a significant advance considering that now the lowest measurement we have is 18 kilometers. Navigation, JPL is building a CubeSat transponder that's currently flying on Inspire that can do ranging and Doppler. Obviously, we will need DSN, which is expensive, but there is a Berkeley 11-meter dish that's available for telemetry. Okay, getting to the moon. So here's kind of where the trade-offs come in and the partners come in. There's 2 ongoing mission CONOPS that have been proposed. One is that there's one CubeSat that rides along to GTO, kind of on a telecom satellite, fits in wherever it can, and then gets ejected to GTO and spirals out to the moon. The second one, and this one is a higher dollar concept, is of a planetary hitchhiker where you have a mothership that ejects multiple CubeSats over the moon, but that obviously requires a lunar-centered mission concept. So kind of right now we're focusing on the ride-along, so there'll be one CubeSat impactor, and that's where the propulsion system comes in. So the propulsion system is being designed by MIT, and it's actually really interesting. Plasma propulsion is very efficient, but it's highly complex. However, the MIT is working and has developed under a number of SIBRs a propulsion system that could work for our mission concept. I'm by no means a propulsion expert, so I'm going to attempt to explain this. You can tell me how good a job I did. But there's a liquid salt that will serve as our fuel. It's low volatility. It is liquid. It will stay liquid. And essentially, it works like a tree pulling water from the soil. Those little bits of liquid soil will travel to the tips of these wicks, at which point a voltage will be applied across, and it will create ions that go across the grid that you see on the lower right. It's going to create a specific impulse of about 2,000 seconds. Now, some of the limitations, obviously, that become apparent are that that's a long time to be spiraling out. So we did some SDK trajectory simulations to see what the power and what the time involved would be. So we're looking at about 30 watts of available power, which is well within a 3U range. We're looking at about 105 days and 1.9 kilometers a second of delta V to go from GTO to lunar transfer orbit. About 400 grams of propellant. 0.7 U of volume. So it's not bad. But obviously there are multiple challenges. This plasma has to fire for between 1,800 and 2,200 hours to get to the moon. So that's a long time. So MIT is doing an aggressive testing campaign right now to see if their system can hold out for that long. So the question is now, can we do that for long duration propulsion system operation? Radiation mitigation along the way. Obviously, if we're starting at GTO, the radiation mitigation is easier, but it's still a complex problem. However, this technology is nearly ready to fly. There's new near-surface measurements that become viable through this technology. And the hope is to impact Raynor gamma and figure out from the high-frequency magnetometer readings that we get back, what is the origin of these lunar crustal magnetic anomalies, which is really the first lunar mystery that emerged back in 1959. So that's the goal of this mission. What's interesting is that the other theory, so I talked about the solar wind flux theory, then there's also the impact theory, right? That there was a giant basin impact on the other side of the moon that created these crustal magnetic anomalies that now results in the swirls. What happens now when we impact the swirl? What's the long duration impact of that? So there's a lot of interesting science that can be enabled through this concept. The only question is, how are we going to get there? That's all I got. Any questions? I made it through without losing my voice.